Hi, this is another video on how to calculate area moment of inertia of a composite section. It's going to be an abstract one. It's not going to be structural steel. It's just going to be a couple of common shapes, circles and rectangles specifically. And of course, part of the deal here is you can't calculate the area moment of inertia unless you also know the centroidal axis locations. So I'm going to randomly pick one here. I'm just going to randomly make one, if you will. And it's going to have a void in it, okay? It's going to have an empty space. So let's just say it's a rectangle. Randomly just making it up here. Let's make a rectangle. Let's do it in inches here. 10 inches high, okay? And that's what, 5 inches like that, okay? But let's put a hole in it, okay? And let's put the hole offset a bit. I should do it in the center, okay? But not in the center of the whole thing. That would be a non-issue. Let's put it up to the top like this, and let's make the hole, I don't know. Okay. All right. Let's make that, so this is 10 inches total height. This is 5 inches wide. Let's make this 2.5 inches to the middle. And let's make it 3 inches from the top, like this. And let's make that hole, trying to keep the scale reasonable. That looks to be, if that's 10 inches, that hole's about 3.5 inch diameter. Okay. All right. Required to find horizontal centroidal axis. That's one. Area moment of inertia. Area moment of inertia about a horizontal axis. About horizontal centroidal axis. That's 2. And 3 is area moment of inertia about vertical centroidal axis. Okay. All right. Again, you can't do any area moment of inertia calculations unless you know where the centroid is. Okay. Now, I made this thing symmetrical about a vertical axis. Okay, the hole's right in the middle. So the vertical centroidal axis is right in the middle. That's not difficult. Okay. But the horizontal centroidal axis is probably, well, it's clearly not in the middle of the rectangle because this is a void. This is missing area there, and it's an area moment balance, if you will. So it's going to be below the midpoint. It's going to be in the middle for sure of the vertically, sorry, horizontally, but it's going to be below, and it's going to randomly draw it here just as a placeholder. Okay, and then again, we want the bottom to be the datum. That means y bar is going to be like that. Okay. And that, of course, will be axis XX in our speak. Okay, axis YY will be this axis here. Y, Y, like that. Okay. So step 1 is to, I'm going to tackle this in order here. Horizontal centroidal axis, step 1. Okay. Well, that's Y bar. Sum of the area I, Y bar I, over sum of the area I. Okay. And I'm going to do it right here. There's no point, stretching it out too far. But all right, now it's true. What you want to do is you want to split this up into easily handled simple shapes. In this case, it's a rectangle and a circle. It's 2 shapes. Okay. So let's call the rectangle R for rectangle. Okay. So it's area rectangle y bar rectangle plus area circle y bar circle. More about that plus in a second there. Okay. And then sum of the, and I'm sticking with this summation. Summation means adding them together. So there's my addition there. But there's a speed bump here coming up. Okay, area rectangle plus area circle. Okay, the speed bump is this. The circle is a negative area, if you will. It's a void, so it's going to have a negative area. All right. So I'll just say, but circle is treated as a negative area. So, okay. So now whether you put the negative there or whether you put the negative in brackets, I'm going to preserve this, but it doesn't really matter how you do it mathematically. But okay, area rectangle. All right, y bar equals area rectangle. Well, 5 by 10. 5. I'm going to leave the units off. The units are going to be all inches. Okay. Area rectangle 5 by 10. Y bar rectangle. Now just imagine if the circle wasn't there. This is how you have to parse these questions up. You have to say, okay, you have to be ruthless in your separation of tasks here. The task with the rectangle is to process the rectangle as though the circle weren't there, as though there was no hole in there. Well, that Y bar is 10 by 2, 10 inches over 2. In other words, 5 inches. It's halfway up. That's here in our right. Here it is here. Y bar rectangle. It's the halfway point right there. Okay. I'll squeeze it in here. Y bar rectangle right there. 5 inches. Okay. I made it 10 by 2, so you see where I got it. Okay. Plus area circle. Well, the area circle is a negative area. Right. Pi by 4. Diameter circle squared, 3.5 square. That's the area of the circle. And Y bar circle, well, that's given. It's 7 inches, right? Y bar circle is the center of the circle. As though the circle were just by its lonesome. Its centroidal axis, aka its Y bar, is right in the middle. Okay, Y bar circle is over here. I'll carry on with this red nomenclature, but here's Y bar circle. Y bar circle. Okay, Y bar circle 7 inches. Okay, and then on the bottom, area rectangle, again, you just pick them from the top. You've got area rectangle, 5 by 10. Minus, this is the thing, the circle's a void, so I got to subtract it. Minus pi by 4 times 3.5 squared. And it becomes a one-liner calc, really. Like when you get going on these, it becomes a one-liner calc. Like you just do it in one line like that. This is fairly simple. All right. I like to start in the denominator. Just don't get tied up on how I do things, but I like to start down there. Saves me having to do brackets. I first go through 4.523. Just going to make a note of that. 4.523. Do it one more time. I'm not working off of a solution here, so I'll do it one more time. Okay. Yeah, 4.523 inches. Well, that's what we expected. It also, judge your answer if you're able to on the validity of it or the sanity check. It's going to be below the 5-inch point. I kind of exaggerated it here, but 4.523. Okay. All right. Moment of inertia calc. About the horizontal axis. Well, we've got that axis. Let's make use of it now. The moment of inertia of this section. This could be an aluminum extrusion or something. You want to know the moment of inertia of it for purposes of a bending stress calc or whatever. Okay. All right. It looks like this. IX. Because normally you draw the horizontal axis when you denote it XX. So IX is the moment of inertia of the rectangle. Okay. Now we need the parallel axis theorem here because the moment of inertia of the rectangle is as though the circle didn't exist. Well, its centroidal axis of the rectangle doesn't coincide with the centroidal axis of the whole thing. That's why you need parallel axis. The centroidal axis of the rectangle is right here. It's right here, right? And so we have that distance separating the two, and that distance is a rectangle dr squared. Okay, I need that. I need that parallel axis theorem. Okay, plus the circle's contribution. Now the circle, well, it's a void, so it's actually going to be a negative value, and I probably should have put that here. Maybe I will, without making too much of a deal out of it, or maybe I won't. I'm working in pen, so that's my bad. We'll leave that the way it is, but it's this is negative. Okay, well, I circle plus area circle d circle squared, and by the same argument, the circle centroidal axis also does not coincide with the component centroidal axis. Therefore, we have that displacement here. I'm going to draw it in blue here. Okay. Here's d circle. Okay, right there. There's d circle. There's a separation between the circle centroid and the component centroid. And here's d rectangle. Now, I agree the diagram's getting pretty busy. And you could make another diagram down here, but I chose not to. This should be negative. Hey? Okay. Circle is a void. Okay. All right, here we go. Okay, I'm going to move this up a little bit. Oops. Let's keep the world lined up here. Here we go. Okay. Ix equals I of the rectangle. Well, 1/12 base height cubed. Okay. The base aligns with the horizontal axis. The h, the height, aligns with the vertical axis. So the base is 5. Okay. Again, as though the rectangle didn't have a hole in it. Right. 1/12 base is 5. Height is 10 cubed. That's I rectangle. Plus area rectangle. Well, that's 50. 5 by 10. And the distance between the rectangle centroidal axis and the centroidal axis of the part, well, it's this little gap right there. It's 5. 5 minus 4.523. And don't forget to square it. Okay. That's the rectangle's contribution. Okay. Minus I of the circle. Well, the circle by itself has a moment of inertia of pi r to the 4th over 4. Okay. Or pi d to the 4th over 64. I'll use this one. Okay. Pardon me. Pi by 4 r to the 4th. Radius 1.75, right? 3.5 by 2. To the 4th. Don't forget that. Don't square it. Plus, now don't put another negative there. You'll double account for it. The negative's outside of the bracket here. So plus the area of the circle. I never figured that out directly, but I'm going to do it right now offline or quickly. Okay. 3.5 squared times pi divided by 4. 9.621 is the area of the circle times the distance between the circle centroidal axis and the part. Well, that's, what is that? 7 minus 4.523. 7 minus 4.523 squared. That's a 7 right there. Okay. Close bracket. Ix equals. Okay. So that's 7 minus 5.423. That's this gap right here. That's this gap DC between this axis and that axis. Okay. All right, here we go. Calculate that one. Okay. It seems weird, maybe. I'm going to do it backwards. I start here and then do it backwards. So it just saves me having to do a bunch of brackets. 7 minus 4.523. That's a negative value. Negative 66.396 is the circle's contribution, plus the, I better actually do it like this. I'll do it like this. Here's the circle, 396 inches to the 4th, okay, and the rectangle. 428.043 inches to the fourth. One more quick check, okay? I always do checks. Whoops. Yes, 428.043, and the bottom one, the circle. Yeah, negative plus 428.043. Moment of inertia, 361.65. That's plenty of resolution. Okay, that is the moment of inertia about the horizontal axis. The centroidal axis, or the vertical axis moment of inertia, is a bit different. It's the same but different. It's you know, if you flip the page sideways, well, the main difference. Well, I better do it. It does definitely warrant another diagram. There's no doubt about it. Okay, so step 3. In other words, however you draw it, lay it over like this. You don't want to use the same diagram, I don't think. That would not be a great place to go. Let's put the circle down here. Okay, like that. Same dimensions. This is 3 inches. This is 2.5. Of course, the whole thing is 5 inches. And this is 10 inches. Now you have to keep your head on straight. The centroidal axis location is going to be just as much work. Sorry, that's a dumb thing to say. The centroidal axis by inspection is right here. The centroidal axis is right. Yeah, there you go. The centroid, as we know, is down here somewhere, but with regard to this axis, which is the YY axis, you know, in previous, you know, per the previous drawing, right? I went and flipped this thing, so I wouldn't call it XX again. I'd call it YY. I just rotated that thing like this, okay? I'm going to call it IYY like that, okay? By inspection, centroidal axis is at Y bar 2, or sorry, this is X bar, okay? All right? By inspection, due to symmetry about that axis, by inspection, X bar is 2.5 inches. Okay, it's right in the middle. Okay, so then I don't need to calculate the centroidal axis. It's an easy one. Okay, now IY, the moment of inertia about that axis, is I of the rectangle, and I'm going to put the negative here, minus I of the circle. Note, I don't need the parallel axis theorem here. I do not need it, because the centroidal axis of the rectangle and the centroidal axis of the circle coincide with the centroidal axis of the whole component. So I get off easy here. I don't need the parallel axis theorem. There's only one centroidal axis. All 3 components, all 3 shapes. Sorry, yes, all 3. The rectangle, the circle, and the whole thing have the same centroidal axis. Okay. No parallel axis theorem needed. Okay, so IY is I of the rectangle, 1/12 base height cubed, minus I of the circle, and that's the same moment of inertia. Pi r to the 4th over 4. Pi over 4 r to the 4th. Notice though that B and H flipped now, so you're not out of the woods yet, okay? B and H here, well, they don't really flip. It just looks different. But now my base on the horizontal is 10, okay? So IY, 1/12. Well, the base is now 10 inches and the height is 5. Okay. minus pi by 4, and the radius is 1.75 to the fourth. Okay, IY equals. Okay, so it's pretty. There's really not a lot of debate. You just have to be, again, ruthless in separating or otherwise logically accounting for the various shapes. All right, here we go. 12 invert times 10 times 5 to the power of 3 minus pi by 4 times 1.75 to the fourth. 96.8. 800 inches to the fourth. One more time, just to confirm, okay? 12 invert times 10 times 5 to the third power minus pi by 4 times 1.75. Okay, yeah, 96.8. That's it. That's the moment of inertia in the x direction. Much, well, in the about a vertical axis. Okay, much easier than the other one because there's no need for a centroidal axis determination. You just observe it, and there's no need for parallel axis theorem. So, okay, that's the two together. Try it yourself. Maybe make a similar question, or just try this one without the solution running. Okay, you take care.